Okay, for this week we'll continue the section that we covered last week. It's actually on the non-destructive test. Okay, as I explained before, the destructive test is primarily for testing that will destroy the sample. That normally will lead to the destruction to the sample, and the sample will no longer can be used. Again, both non-destructive or destructive, they are both for to test the practicality, the effectiveness, the functionality of the mainly on the insulations. Okay, and the same goes to this non-destructive test. It is also to check for the functionality or to check for the defect of the insulation materials. Okay, so that we know the quality of the insulations, so that we know the any damage, anything that related to the performance of the insulations before it been used in practice. Okay, and this for today we will talk on these two commonly used tests for the non-destructive. First is Schaechering bridge, and then the other one is the partial discharge measurement. Okay, sharing bridge. Okay, sharing bridge. It is actually this circuit. Okay, this circuit is actually what we call it as a tan delta test. Okay, tan delta, or also known as dielectric loss, or also known as dissipation factor. They are known as the tan delta test. Okay, tan delta test ni, okay, the higher the tan delta values, means that it indicates that the values of the dielectric material is lead to that will lead to the worst condition, the worst insulation conditions. The higher the value, the poor the performance of the insulator. Okay, the lower the better, the higher the worst conditions. Right, because variation or the tan delta value of the tan delta or dissipation factor or dielectric loss can be affected by also the applied voltage and any internal discharge activities. Okay, it can be affected by this scenario. Okay, let's see on the, okay, this is the general circuit representations. It composed of we call it this one high voltage sharing bridge. Okay, we have it composed of arm 1, arm 2 here, kalau if you can see here, and then arm 3 and arm 4. Okay, it composed it, and we have in the middle as the device or known as detector. Okay, okay, we can see here, okay, the sample of the dielectric. Okay, the sample of dielectric will be placed at arm 2. Okay, it is a combination of Rx and Cx. Why? Because the insulation material is normally referred as the capacitance values, right? And the resistive, if to values resistive component is normally reflected to the failure or to the any aging or any deterioration of the insulation levels. Okay, we have the first arm. Okay, first arm, second arm, third arm, and fourth arm. Arm 4. Okay, generally for arm 1, 3 and 4, they are standard. They are standard arrangement except for arm 2. Okay, arm 1 filled with the gas capacitor. Arm 3 is variable resistor. We'll place here variable resistor, and arm 4 is with variable capacitor in parallel with R4. The idea of this variable is for us to change the values, so that we can change the values so that in order to trigger for the detector. So we don't have the fixed values. Sometimes the current is very low, we have to increase or decrease accordingly. Okay, so at least you know the arrangement or the circuit diagram for the sharing bridge to conduct for non-destructive insulation test, or we use this one for tan delta to know the deterioration of the insulation values. Okay, in practice, okay, this is the how we can calculate for the tan delta. Okay, how we can calculate, we use the formula as tan delta is equal to omega cx rx equal to omega c4 and r4. So means that the parameter that will determine the tan delta will directly affected by the value of c4 and R4, which is in the arm 4. Okay, arm 4, they are arranged in parallel conditions, right? Okay, this is how they calculate by formula. And then now we go to the second non-destructive test, which is the partial discharge measurement. Okay, this is the most popular, okay, the most popular non-destructive test that been implemented in practice. Okay, people or researcher are very keen to look on the partial discharge measurement. Okay, because this one is just on the tan delta dielectric loss, the capacitance, but this one the researcher is looking at the any premature activity that may lead to the discharge or total failure or flashover. Okay, partial discharge measurement, as what reflected by the title here, discharge. We know discharge activity is actually the breakdown in the air. Normally breakdown values, breakdown voltage values in the insulation material. What is meant by partial discharge is it is not total breakdown, but it just initiation. The initiation of the breakdown means that we can see, if we can see on the surface of metal, it'll become like a spark, a spark on the surface, but it will not break down between two conductor, two electrodes. Okay, it just on the surface, it's just within the material that wouldn't cause any problems, but we can see the discharge activity, but it not lead to the total failure or total what we call a flashover within the material. Okay, see, the term referred to the discharge activity that not completely breach the space between electrode. It is only partial. We have two electrodes, it only halfway or partially between the two electrodes. It's not affect, or it will not lead to the failure at this stage, the mechanism. Okay, and how it is measured, either by electrical pulse, acoustic emissions, and then this is normally been converted into the probe or measurement device. What we use in practice, for electrical, we typically use the electrical pulse. We will see the waveforms, the pulse activity, and from there we will interpret. Later on I will show you on the YouTube the example what is meant by partial discharge and how we're going to measure it. Okay, right, and then okay, next, okay, we have several categories of partial discharge. First, we have internal discharge. Internal discharge, we have the solid insulators, but we don't know what is inside the insulators, right? Somehow during the manufacturing process there are little void. This is what we call it a space, a void, a small gap, a small void within the materials, And then during the manufacturing process, means that it's not fully, it is not fully occupied with the insulator. That's why during the manufacturing process, most manufacturer normally will fabricate the insulators, the one that you buat project tu, you compose the project. Normally they will fabricate within the vacuum, in the vacuum chamber, so that they can actually avoid or eliminate the effect of void. They don't want any hole, any small hole within the insulator. Okay, that is internal discharge due to void. And then we also have a surface discharge activity. Okay, we have two conductors, and then there might be a surface discharge activity between this conductor, but it not lead to the flashover, but it's still the corona activity. And last is corona discharge, or treeing corona on, as what we can see in the gas. Okay, again, partial discharge mean is not the total failure, it's just the initiation of the discharge activity. Okay. Okay, what most important, why we interested with the partial discharge activity? Because it is directly proportional to the dielectric lifetime punya estimation. Okay, so means that once we evaluate any insulation device, we should evaluate for the partial discharge activity, and from there we can tell whether the insulator is healthy conditions or in the sick condition that need to be replaced. Okay, later we'll show you how it's work. And then okay, the problem related to partial discharge. Okay, partial discharge is very crucial. Nonetheless, it is very difficult. Okay, it is very difficult to capture. It is very difficult to measure, and it is very difficult to address the problems. Okay, first measurement of PD is not easy because it deals with the noise. Okay, because when it's happened inside the dielectric, sometimes it will greatly affected by the noise. Okay, the result also may be disrupted by the noise as well. Okay, so we couldn't, it's very difficult to differentiate whether it's the noise or it's the partial discharge. Okay, and another thing is occurrence of partial discharge activity will be normally self-extinguished. Okay, it'll be come and go, kejap ada, kejap tak ada, kejap ada, kejap tak ada. So it's a great challenge for us to detect whether this is really a partial discharge that cause a problem to the high voltage insulations, or noise, or is not. Okay, or it is a good insulator. So these are among the very challenge to the researcher to deal with the partial discharge. Okay, concept of measurements. Okay, concept of measurements. If we look at this point, okay, okay, if we look at this point, we have two electrode here. Okay, electrode, and we have dielectric materials, and we have a space here. Okay, what will occupy the space, the gap or the void here? It should be, normally it should be air. Okay, it should be air. And then what will happen? We will represent this arrangement into circuit representations in terms of capacitance A, B. Okay, capacitance A in parallel to B and C. This is reflected by the gap, by the air, by the insulations. So we will determine the voltage drop across this void. Okay, so it should lead to a calculation equal to EC. Okay, the electric field strength, macam kawan-kawan tanya tadi. Amsyar tanya tadi, electric field strength, electric field intensity, sama lah tu. EC equal to permittivity, relative permittivity times electric field at around the area. Okay, E capacitance is equal to relative permittivity times electric field of the around the area. Okay. Okay, what will happen? Okay, what will happen? What will happen if if the electric field strength in the cavity, in the void, in the empty space here exceed the gas material breakdown strength? Maksudnya means that if we have electric field or exceed the electric breakdown here, then it will occur the discharge. Okay, discharge just within this small area. Okay, it's not within the materials, it's not between the two electrodes, but it just happened within this material. What will happen if the discharge start to happen, if the partial discharge start to occur due to heating, due to heat of the from the discharge, that may deteriorate the dielectric material here, and it will generate first byproduct gas, byproduct gas within the void, and it will cause damage internally to the materials, and then this will cause a cascaded effect or domino effect. Once the byproduct gas that have even lower breakdown values, and then more and more breakdown activities will happen within this void known as partial discharge, and that eventually will lead to the failure of the insulator. Later on we'll show you example of the videos. Alright, these are the one that I just explained to you. You can read yourself. How is the partial discharge? We have the two terminal, electrode and ground, means that whenever we see any discharge activity around the surface, that is what we call as partial discharge. When it's happened across the two electrode, then we call it as flashover or full total discharge. This is partial, this is full. You can read. Maybe it's worth to show you a video, this one. Sekejap. Hold on. Okay.
The continuous and high-quality supply of electrical energy is at the heart of our modern economies. Engineers around the world work hard to make this power supply reliable and safe. All major power supply components, such as transformers, cables, generators, and switchgear, need to be kept in perfect operating condition. Their insulation must be able to withstand high voltage stresses. Therefore, it is crucial that its condition can be verified.
This one adalah contoh total flashover. This one adalah we have the insulator. We have the insulator here, and then under adverse conditions, at any under humid, under raining condition, under wet fogging conditions, this problem might happen. That will cause outage. That will cause a problem. These are the thing that power utility try to avoid. Kenapa? Why?
Therefore, it is crucial that its condition can be verified throughout its life cycle. A partial discharge, or PD, is a localized dielectric breakdown of a small portion of the electrical insulation. It can be initiated by voids, cracks, or inclusions within a solid dielectric, at interfaces within solid or liquid dielectrics, in bubbles within liquid dielectrics, or along the boundary between different insulation materials. PD causes the insulation to deteriorate progressively and can lead to electrical breakdown.
Okay, after some time, if we going to have a continuous partial discharge activity within the insulation material, that will lead a total failure, this kind of thing, like this one cable, failure of the insulation.
Insulation breakdown can lead to dangerous situations, severe damage, and ultimately huge economic losses. The affected component needs to be closely analyzed to make sure the PD will not lead to further damage or even complete destruction. Therefore, the integrity of the insulation of high-voltage equipment should be confirmed.
Okay, if you can see here, this is how in the laboratory people testing for the partial discharge activity. So actually this one is the, what do you call this one?
Make sure the PD will not lead to further damage or even complete destruction.
Okay, this is the signal that detected from the partial discharge activity, and from there, they will interpret it whether the condition of the insulator is a good or is or it need to be replaced. Okay, PD can be will be conducted primarily on the transformers, windings, insulations, and very important element of power system.
Therefore, the integrity of the insulation of high-voltage equipment should be confirmed using PD analysis during its manufacturing, its commissioning, and during its lifetime, so that it stays in good condition and is safe to operate.
Okay, this is one, and I would maybe this is one. I'll show you the video here is for you to easily digest what is actually the partial discharge and why it is very important to know or to
What is partial
identify or
discharge?
to measure.
Partial discharge, or PD, is essentially a spark that occurs in defects in high-voltage electrical insulation. It's called a partial discharge because the discharge only partially bridges the gap between the conductors. The discharge may be in a gas-filled void in a solid insulating material, in a bubble in a liquid insulator, or around an electrode in gas. In high-voltage cable systems, PD is commonly found in joints and accessories, where a defect or void exists. These are caused by incorrect installation or long-term degradation of the equipment. In switchgear, cracks and voids in insulating materials and components causes PD internally. Contamination on the outer surfaces or incorrect installation of insulators, bushings and terminations will cause surface PD. Partial discharge is generally accepted as the predominant cause of long-term degradation and eventual failure of electrical insulation. According to research, 80% of high-voltage failures occur due to asset damage caused by PD activity. PD activity can be monitored on in-service equipment to reduce these failures.
Okay, based on we know here, it is about 80% of high voltage failure is from the PD activities, partial discharge activity. So we really need to measure, to monitor, to ensure the reliability of the insulation material remained in a good conditions. Okay, that's about the PD, and then probably I'll just show you a couple more videos here, one or two before.
इसे माप इस गैप को मापने के लिए
Okay, this one, this group of researcher, just to explain to you, is going to conduct a healthy test or test on the transformer oil. Okay, what they do, they need to set the electrode at certain values. Okay, this is how they take the transformer oil. Okay, to test the transformer oil. This is really I have the experience here for taking the transformer oil for testing at the Petronas. We did the same. First, you need to have the container, and then you need to wash the container with the insulation with the oil there from the transformers, and then you need to fill up the bucket, or you need to fill up the container full with the water, with the transformer oil, to make sure it is fully covered to the electrode. This researcher try to fill up with the transformer. We'll see. This is the actual transformer, and this is the actual what will happen in practice. Why is a transformer oil? Because transformer oil is a liquid insulation material, as we discussed before about the breakdown, about the breakdown phenomena in the liquid electric. This is kind of backbone of the transformer. The insulation is very much important. Okay, so now is fully covered the electrode, and then we will close it in the container. Okay, we close it, we close the tank. Okay, now we will take the transformer oil into the test rig. Okay, we will place the box, the small box, the mineral oil just now into these two electrode, and these two electrode will be connected to the high voltage and the ground. Okay, so where is the circuit? Circuit is within this test set. Okay, the test set, it is a dedicated made for transformer oil for insulation testing. Now we apply the voltage, switch on, and then we will gradually increase. Let's just see this one. Okay, this is a transformer, you can see. So kita akan run, kita akan perform BDV. What is BDV test? Breakdown voltage test. That is, we call it as BDV. Okay, breakdown voltage test. It's okay, I think the video here kind of lag. Okay, and then so basically that is how and they conduct the test, and how a little bit with the illustration. Video illustration is very good to improve for a good understanding. So we can really see what is the importance of the partial discharge activities and how we measure it. Okay, how we measure the partial discharge. I think there is one video about the how to measure partial discharge. It's okay, later on. Alright, now we complete with the non-destructive test. Okay, sharing bridge, and the other one is partial discharge test. And now we come to testing of dielectric materials. Okay, testing of dielectric material. How are we going to perform the test? By using HVAC, HVDC, and HV impulse, or what we call it, HV impulse voltage source. Okay, 3 type of voltage tests that we normally execute in the lab or in practice. Okay, right. HVAC test. This is also known as a low frequency test. Why? Why is low? Because HVAC is related to 50 or 60 hertz. That's related to the power frequency, and HVAC is related to alternating voltage. As we discussed before, alternating voltage is going with the sinusoidal wave. As compared to HVDC, we have constant voltage level at the peak values. Okay, and normally for other than 50 and 60, we call it temporary over voltage test. We call it TOV test, temporary over voltage test. Okay, normally when over voltage test, the frequency will be greatly affected. It can be between the 10 to 100 hertz. Okay, for HVAC, we have 3 type of tests. Okay, 3 type of tests. We have the whole scale test, we have a small scale test, and we have a long duration test. Okay, mainly HVAC is used to identify manufacturing defect. Okay, and also we need to evaluate the partial discharge activities within the materials. So that's why we need to perform partial discharge test to see whether the condition of the insulator is good or bad. Okay, so other than that, we need to know the manufacturing defect. If the partial discharge activity within the insulator is very high, so we know there is a lot of void inside the insulator, and we can actually declare that the insulation material is defect, and we can return to the manufacturer. Okay, now we're going to see what is the difference between whole scale test, small scale test, and long durations. Why we need them? Why we need 4? Okay, whole scale test, whole scale insulator test means that we perform the experiment or the testing on a full scale of the insulator sample, ready-made product. So means that after it's been successfully manufactured, we have one whole unit, and then we test it as a whole unit. That's why we call it as a whole scale test. And then of course, as what we discussed before, we can run the test under dry and wet conditions, because insulator normally will use it outdoor. So we need to reflect the real scenario in which sometimes they are dry and sometimes they are wet. So we need to do both. And this is also we want to see the functionality of the defect test as well, from the manufacturer. Okay, wait. Okay, what is a small scale test? A small scale test, we just take a fraction of the product, and then we test it. Okay, for example, we have the full scale insulator. We cut along a piece of the shed, and then we take for the test. Why? We need to perform the material test, for example. So we need to know whether the characteristic of the material maybe. So we need to verify the characteristic and scientific analysis of that particular material. Okay, normally the small scale test is far more economic. because we don't need to manufacture as a whole product. We just use the material. We just take the sample, and we can actually perform with the experiments. And some more, we don't waste the material. Say for full scale, we have a bunch, and a small scale we can actually just use. Example, we want to check for tracking test, electrical tracking test, partial discharge test, or all of these tests can be done on the small scale insulation test, right? As compared to the full scale. Okay, how about the long duration test? Okay, long duration test means that we want to replicate what happened in practice. Okay, of course. Okay, the insulation material will be used in power system for more than 10 years, sometime up to 20, 30 years. Okay, we don't have such period of time for us to conduct the experiment. All what we can do, we need to do for the accelerated aging test. Means that we going to run the test on the product, the sample, on the product or on the sample at the accelerated period of time. For example, we run it for 1,000 hours. That will replicate sometimes more or less about 10 years in practice. So we apply the voltage. Of course, there are criteria that need to comply. We refer to the standard how we going to run the accelerated aging test or long duration insulated test. So we want to test the durability, endurance level of the device, and under certain condition that can be considered as accelerated aging test. We want to know if we run if we stress up the sample for a certain period of time with a certain duration, certain conditions, that will replicate 1 hour is equal to 1 month. For example, 1 hour or 10 hours is equal to 1 year. So we need to know, or maybe 24 hours. That represent the insulators in practice for 10 years, for example. So this one, long durations test can be done on the full scale or the small scale, and it required a sustainable supply of power supply. Means that we going to run the experiment for 24 hours, for 48 hours. Of course, we need the system in the lab need to be ready. So there shouldn't be a interruption of power supply. Run experiment for 6 hours and then breaker failure. No power supply. Then we need to repeat again. It need to be continuously. Okay. See, the testing could last around 1,000 hours or more, right? So example of this, a salt fog test or atmospheric chamber. This one we want to represent what happened in practice under normal conditions, under normal atmosphere conditions. Okay, so 3 main category of tests: whole scale, small scale, and long durations. So we know the difference of them, and now we come to the HVDC test. Okay, as I explained, this is very rare to be implemented in practice. So it means that we engineers or researchers rarely perform HVDC tests. Rarely. Normally we'll just go for HVAC test. One of the reason is because of the risk, because of it is a DC source, means that we have a continuous supply, and it can be costly. Power rectifier system, we need a rectifier system to establish the DC. This may limited to the small scale project. Kalau when we say for example 100 kV DC, we don't go beyond. We don't go beyond because of the risk of failure, the risk of the disaster, the risk of incident that may lead to the injury or anything. Okay, something similar, damage to the equipment. Because as we mentioned, if we increase the voltage, high voltage DC at the continuous, the insulation may not able to sustain the stress by the DC voltage source, especially at the very high magnitude values. Okay. And then less popular, as I mentioned before, less popular. And then normally we will use on-site testing, highly capacitive load, such as a cable, very very popular. And the last testing on the dielectric material is the lightning impulse test. We call it as impulse test. Impulse test can be categorized into two categories, lightning and switching. We have impulse test, we have impulse voltage, and impulse voltage can be divided into two, lightning or switching. Okay, now this is also very popular testing in the high voltage field. Okay, HVAC and impulse test. Okay, as I mentioned before, impulse tests are categorized into two, lightning and switching. Lightning means we try to replicate the lightning source from the nature, and the switching impulse, we try to replicate the switching activity on and off. As simple as at your home, I repeat again, when you switch on and off, you may, in the dark, you may see the spark as well. Okay, but just imagine what will happen 240 also, we can see the spark in the dark. Just imagine 200 kilovolt, 500, 300 kilovolt. These are a very high value that may lead to the failure. Okay, ni apa pula tiba-tiba. Okay, lightning. Okay, how to differentiate lightning and switching? Okay, lightning and switching, how to differentiate them is just by the waveforms. Okay, lightning, of course, the circuit arrangement will be different. We need to use a different composition of capacitance resistive value to establish the lightning waveforms, and we need to have a different value, different circuit arrangement to establish switching. Okay, what most important, okay, now this one, overvoltage due to lightning is also known as fast front overvoltage, FFO. Fast front, because what happened, the rising time happened at very at a very fast period of time in microsecond, in which the switching activity, we call it as a slow front overvoltage, SFO. Okay, slow front means that the rising time is slower as compared to the lightning. Okay, lightning, as we know, the effect is very instantaneous. So, okay, for a low system voltage less than 132 kV, these are more prone to lightning overvoltage failure, in which above the 132 kV, these are prone to the failure due to switching. Why switching? Because the switching activities for 132 kV and over, that is very serious and severe. In which for the system that less than 132, why it is prone to lightning strike is because the system is 132. So means that the insulation, the protection device is meant for 132. Okay, so when lightning strike, so means that the system unable to sustain with the very high voltage from the lightning. That's why low power system, lower than 132 kV, is prone to the failure due to lightning strike. In which for the equipments, for the power system that greater than 132 kV, we know this equipment is well protected. They are equipped with the very protection device that higher that can really sustain with the lightning strike. Okay, lightning strike tak ada hal, issue, no problem, because they are well protected, except for the switching activity. The switching activity sometimes that can be severe, because this is on and off activities, so we can't avoid that. So sometimes it lead to the failure to the system. Okay, how to differentiate the impulse waveforms? Okay, this is the general impulse waveforms. So we have, if we plot a voltage again times, we will have a quick rising time at this point going to decay time. So this is what we call rising time. This is decay time. So for the switching, the rising time is up to 250 microsecond. Okay. While for the lightning, the rising time is actually only 1.2. It's about 250 times faster than the switching. That's why this one we call it slower, and this one is we call it fast. FFO, SFO, slower front time, and SFO, slow, FFO, fast front time. Okay, so the difference between this one is the decay time is 2500 microsecond, while for the lightning it is 50 microseconds. So these are one of the important difference between lightning versus switching impulse waveforms. Okay, I don't repeat this, you can read just what I mentioned to you. Again, this one you can read the details in terms of the tolerance here, 50%, 100%, you can read by yourself. Okay, and now we come to this one. Okay, since in high voltage application it is very difficult to generate to obtain the lightning or switching impulse, so the researcher or the standard spell out the plus and minus for the front time, and for the switching as well as for the lightning. For lightning, we need 30% plus minus and 20% plus minus for the tail time, T1 and T2. While for the switching impulse, they said as to be 20 and 60 respectively for front time and tail time, T1 and T2. Okay, so this is also another difference between switching and lightning. Okay, example. Draw and label a standard lightning impulse waveform, 1.2 50 microsecond, having a minimum tolerance front time T1 and T2. The peak values is 1050 kilovolt. So you have to draw something similar to this. So you have to draw the impulse waveform. You have to specify what is the V peak, what is the T1 and T2. That's it. Okay, now we come to the lightning impulse test. Okay, as I mentioned, this is a very popular test that be conducted in the lab as well as for the high voltage equipment. Why? Because high voltage equipment, power system equipment normally installed outdoor. We have a power transmission, power distributions, we have a substation. All of these power equipment device are installed outdoor. That's why they are prone, they are subjected to the lightning attack, lightning strike. Okay, so these are the test to test whether the equipment or the device that been introduced able to absorb the stress from the lightning. Okay, it's important for less than 132 kV, as I mentioned before, because this is the term basic lightning insulation level. Okay, basic lightning insulation level, BIL. For that meant for the device is not up to the the typical value of the lightning. They meant for 132 kV, and the lightning strike is far greater than that. That's why they don't cater for higher. Why they don't go for the higher? Because they want to compromise with the insulation level, because high voltage is very expensive. They need to have a very expensive insulations level for 500 kV, which is not very economical. So the device meant for 132, but the insulation protection device, the protective device is made for 150, for 500 kV. That means it is not practical at all. So that's why this one is prone to the failure. Okay, the test. Okay, typically, normally for the lightning test, we conduct for the whole scale or ready-made product. After one full unit, we will apply the lightning impulse to the product. So we normally don't do on the sample on this one, because it is lightning. So really it should be a final or an end product. Okay, positive and negative polarity. Positive polarity is the waveforms going upwards, while the negative polarity, the waveform is going downward. It could happen. It will happen. Sometimes we will get negative, and sometimes it will be positive polarity. And in the experiment, we can actually switch the polarity, but in practice, it is by nature due to lightning strike. Okay, switching impulse. Okay, why we want to perform the switching impulse test? Because this is normally referred to open and off operation during the maintenance service. Okay, as we know, we rarely shut down the power transformer. We rarely shut down the power supply. It will operate 24/7. Of course, in any circumstances, we need to switch off for maintenance purpose. Then the switching will come into place, in which we will switch on and off activities. Okay, switch on and off activities that will lead to the at the substation or the power transformers. That's why we still need to perform the experiment. So this one just now BIL, basic insulation level, and now we call it BSL. Okay, basic switching insulation level, BSL, basic switching insulation level. And again, of course, in the any testing, we need a large clearance. What are you referring to the large clearance? Okay, large clearance means that we have one sample in the middle, and the clearance, the distance between other device is huge, because we expect the magnitude from lightning or switching is very high. That's why we need a clearance. No one can stand. Maybe if we want to inject 100 kV switching impulse, we cannot. We need to prepare the clearance up to 3 meter, 4 meters, and no other nearby device to ensure to prevent a failure. Okay. That's why kalau you tengok dekat substation, we need a very huge space for the power transformer, for the transmission tower. That is for clearance. Okay, the clearance to avoid failure. Okay, what else? Okay, you can read the text. Okay, I think last but not least, okay, we have the standard and non-standard. Okay, we have standard and we have non-standard test, impulse test. What is standard? Okay, what is standard is standard impulse test, the one that we execute. Okay, we execute by using the specified voltage waveform. Okay, what is non-standard? It is not comply to the switching or lightning impulse waveform. It can be the time T1 and T2 is different. The rising time and the decay time is different. That is what we term as the non-standard. That could happen under temporary overvoltage, and again we still need this is not really popular. The non-standard impulse test is not really popular because this is subjected to the uncertainties. Alright, that's about it about the diagnostic testing in high voltage. Okay, do you have any questions, students? Any questions?
No, Doctor.
No? Fully understand, Tanisha?